Would the presenter for the signed SGD paper please come forward? You might be Jeremy Bernstein or Yujing Wang or Kamyar Azizad Nashalali or Anima and Kumar. Do we have a presenter for the signed SGD paper? Okay, great. Well, welcome everyone to this afternoon session on non-convex optimization. I think this is just such a super important topic, and I'm excited that we're really engaging with it as a community. Literally for hundreds of years now, we've been just assuming and acting as if everything was convex, and it's nice to see us really trying to grapple in the weeds of these non-convex problems that we truly have. We'll have 4 talks, 20-minute talks, and we have all our speakers-ish, one of which will be virtual. And so we're going to go ahead and let a couple more people in here and find seats, and then we'll get started. Our first speaker will be Zhang Gru. Zhang Gru is currently at the University of Rochester, where he's working with Ji Liu, and before that was at the University of Science and Technology in China. Okay, great. Zhang Gru.
Thank you. Hello, everyone. Yeah. The title of this work is Asynchronous Decentralized Parallel Stochastic Gradient Descent. I'm Xiangru Lian, and this is a joint work with Wei Zhang, Ce Zhang, and Ji Liu. Okay. Firstly, let me briefly introduce the stochastic gradient descent algorithm with a single worker. Normally, we have a dataset D, and we want to train a machine learning model with parameter of weight X on the dataset D by randomly selecting samples from the dataset. There is a predefined loss function F for the given model and the sample psi. The goal is to minimize the loss function on the whole dataset. That is the expectation of the loss function for each sample. And we often use the stochastic gradient descent algorithm to solve this optimization problem. With a single worker, the update rule for the SGD algorithm is in each iteration, we subtract from the current parameters by learning rate times the gradient of loss function for a randomly selected sample psi. When it comes to multiple workers, we distribute the dataset D to n workers, where the dataset Di is on the ith worker. The goal is to optimize the global loss function, which is the average of the loss function on each worker. When every worker can access all the data so that Di equals D, this optimization problem is the same as the previous optimization problem. After successfully distributing the data, we need to decide how the workers should communicate. One simple approach is to have a parameter server here, which keeps the machine learning model and let all other workers update the model on the parameter server. This approach is easy to analyze, but suffers from the communication bottleneck at the parameter server. And when the parameter server is down, the whole system will fail. Another approach is to connect the workers in a decentralized fashion. Each worker keeps its own local model, and the worker only communicates with its neighbors to update its local model. This is harder to analyze, but it's robust and does not have the communication bottleneck. Our paper focuses on the decentralized topology. Next, let's take a look at the difference between synchronous and asynchronous updates. In synchronous algorithms, in each iteration, all workers need to finish updating to step into the next iteration. So a faster worker has to wait for the slowest worker in each iteration. But in asynchronous algorithms, each worker can continue working without waiting for other workers to finish. So asynchronous algorithm can reduce the idle time of workers, especially when there are some stragglers in the system. And our paper focuses on the asynchronous updates. All the algorithms we will mention have the same SGD's optimal convergence rate 1 over square root of k, where k is the number of iterations. Note that for desired accuracy of the final model, the total time spent on training equals the time spent on communication plus the time spent on computing gradients. The time spent on computing gradients depends on how many gradients we want to compute, which then depends on the convergence rate of the algorithm. Since 1 over square root of k is the optimal convergence rate for SGD, we cannot save much in this term, but we can use in decentralization and asynchronization to save the communication time significantly. We first review how we parallelize SGD using a parameter server. In synchronous centralized parallel SGD, each worker samples from its local data and pulls the model from the parameter server to compute a stochastic gradient here. And the parameter server collects all the stochastic gradients from all the workers in each iteration and update their average into the model to step into the next iteration. The same update rule can be implemented without a parameter server using our reduce technique. When we are using parameter server, for n workers, the latency cost, which is the number of handshakes at the parameter server per iteration, is proportional to the number of workers, that is On. And the bandwidth cost at the parameter server, which is the number of models or gradients transferred per iteration, is also proportional to the number of workers. Also, there is synchronization in each iteration, so faster workers has to wait for the slowest one. By using the all-reduce technique, we can reduce the bandwidth cost to a constant per iteration. In asynchronous centralized parallel SGD, every worker blindly pulls the model from the parameter server and computes a gradient. Then the worker updates the model in the parameter server using the local gradient. However, when worker is computing a stochastic gradient, the model in the parameter server may have been modified by another worker. So in fact, here the worker may be computing a gradient based on a stale model. In this case, faster workers do not need to wait for any slower worker and can continuously update gradients. The latency cost and the bandwidth cost for this centralized asynchronous SGD are not changed. But since the algorithm is asynchronous now, there is no synchronization, and the idle time is reduced. In synchronous decentralized SGD, the workers are connected in a decentralized fashion. For example, they can be connected using a ring network. Each worker has its own local model, and they can be different. In each iteration, each worker samples its local data and computes a local stochastic gradient based on its local model. So there are n local stochastic gradients here. And then each worker will average its local model with its neighbors here. And finally, every worker will update its local stochastic gradient into its local model. For this algorithm, the latency cost and bandwidth cost at the busiest worker are both reduced to a constant per iteration. But there is synchronization, and faster workers has to wait for the slowest one in each iteration. In this work, we managed to use both asynchronization and decentralization to parallelize SGD. In this algorithm, every worker first compute a stochastic gradient based on its local model, which could be a stale model, because when it is computing the gradient, its local model could be updated by its neighbors. Then the worker will average its local model with a randomly selected neighbor. And finally, the worker will update its local stochastic gradient into its local model. In this way, a fast worker does not need to wait for all other workers to finish to step into the next iteration. And the latency cost and bandwidth cost are still low because we are still using decentralization. However, since when a worker averages its local model with its neighbors, it needs to modify its local model and its neighbor's model atomically. This may introduce deadlock. For example, worker A send its model to B, and with B to send B's model back to average. But B has already sent its model to C, and waits for C to send back C's model to average. And unfortunately, C has sent its model to A. We can avoid this deadlock by labeling workers as active workers and passive workers. Active workers are only connected with passive workers. They all update gradients, but only active workers ask neighbors to average, while passive workers only accept averaging requests from active workers. In this way, there is no longer deadlock. Intuitively, we can think of the passive workers as many local parameter servers. We also provide theoretical guarantee for our algorithm. The following assumptions are used. First, the loss function on each worker has Lipschitz gradients with Lipschitz constant L. And secondly, the loss function on each worker had, secondly, the communication graph has a spectral gap controlled by a constant rho smaller than 1. Note that any connected graph satisfies this assumption. And third, the stochastic gradients have bounded variance. And finally, the stillness of the models used for computing gradients are bounded. We then have the following theorem showing the convergence rate. With appropriately chosen step length or learning rate and a sufficiently large number of iterations, the algorithm has a 1/square root of k, where k is the iteration number, a Gordic convergence rate. Note that the resulting model of this algorithm is defined by the average of all models in all workers. And this convergence rate is consistent with the optimal SD convergence rate, and it indicates linear speedup with respect to the number of workers, since how fast the number of iteration increases is proportional to the number of workers. Finally, we did some experiments. First, we compared the convergence rate of all reduced, that is the centralized SGD with all reduced optimization, and decentralized parallel SGD, which is DP-SGD. This is synchronous decentralized SGD. EAM SGD is a version of asynchronous centralized SGD. And ADP-SGD is our asynchronous decentralized SGD. So for both VGG and ResNet20 models on C410 dataset, with respect to epochs, ADP-SGD does not sacrifice the convergence rate and converges similar to RDS. When it comes to the case that there is a slower walker, figure 3 shows that all synchronous algorithms, including DP-SGD and RDS, are significantly slower than ADP-SGD. And figure 4 shows that if there is a slower network link in the system, the centralized asynchronous SGD is significantly slower than ADP SGD. So ADP SGD is robust under heterogeneous environments. We also conducted experiments on ImageNet with ResNet 50 model, and the result shows that ADP SGD can converge to a similar result with respect to the number of epochs as synchronous centralized algorithm up to 128 workers. We did this experiment for ImageNet on a shared HPC cluster, and we plotted the time used for training in each epoch. The result shows that ADP SGD can be orders of magnitude faster than other algorithms due to its robustness against any slower worker or network links. And thanks. Our poster will be at Hall B, number 86 tonight. And I'll take questions.
In case you couldn't hear me, we have time for a couple of questions if people could come up to the mics. While we're waiting for people to be less shy. So Zhengru, what I liked about this was that you're kind of blending decentralized and centralized by having these passive passive local parameter servers, if you will. Have you guys experimented a lot with different sort of network architectures for that, or the probability distribution over passive versus active, or do you feel like there's a lot of room to sort of think harder about those questions?
Yeah, actually, a ring network is not optimal for this decentralized algorithm. And there's some more sophisticated construction networks to make this converge faster and more efficiently. But that's too much for the slide, so please read our paper.
Hi, thanks for the talk. Just as a follow-up to that question, what about adapting the network on the fly and possibly relabeling the nodes?
The only assumption on the network is that it is bipartite graph, so that passive workers are only connected with active workers. And definitely we can change the network connection on the fly. That's not a problem for the algorithm. And it could be some benefits for some applications.
Since you have many local parameter servers in the decentralized version, so when you do the test, how do you combine so many local workers?
So we have a theorem indicates that actually the models on all workers will converge together eventually. So during the training, we often test using the model on one worker. But at the end of the training, if we want to use a final model, we will average the model on all workers at once to get a final model.
Thank you.
I have just a small question related to the scalability of the method. How much is scalable toward, maybe 100 of workers or something like that?
Yeah, we did this on 128 GPUs, but we didn't try higher numbers of GPUs.
Okay, thanks.
Yeah.
Quick question. Does the step size depend on the number of workers?
Yes. So if you have a higher number of workers, we tend to choose a larger step size on each worker because intuitively, if we update a stochastic gradient on one worker,
Sorry, I think you mean smaller step size if you have a lot of workers, no?
Yeah, I mean, if we have more workers, then on each worker, the step length will be larger, so that eventually the larger stochastic gradient updated in the local model will propagate to the whole network, and the effect will be a smaller learning rate on each worker.
Unfortunately, we'll have to take the rest of the questions for the poster this evening, and I'd like to invite Jeremy Bernstein to come up. Thank you.
Thank you.
Jeremy joins us today from Caltech, and he'll be presenting on work with his advisor, Nima.
Thank you. Oops. Hi. This is joint work with the really great collaborators you see on the slide. So SignSGD, compressed optimization for non-convex problems. Okay. So SignSGD is an algorithm which just takes the sign of the stochastic gradient, just sets the gradient components to plus or minus 1. It's compressed, which can reduce the communication time in distributed learning. And we study non-convex problems because they're the realistic ones for deep learning. Okay, so here's the structure. First of all, I'm going to tell you why you should care about this algorithm. And the claim is that everybody here should care about this algorithm for one reason or another. We'll give some theoretical results, and the results will be interesting in a particular regime. And interestingly, this regime, as we're going to empirically characterize neural networks, I claim is really relevant for deep learning. So the algorithm should be good for deep neural networks. And then finally, we'll show you that the algorithm does actually work on ImageNet, and you can train an ImageNet model using this algorithm. So why care about the algorithm? The first reason is gradient compression. So as mentioned in the last talk, one common way to train neural networks today is to distribute learning over GPUs, split the data across the GPUs, evaluate gradients on each GPU with respect to the data on that GPU, and then send the gradients up to the parameter server. Then add them up on the parameter server and send them back down. You can see there's a lot of communication going on. Every step of the algorithm, communication of gradients happens. So if we can compress the gradients, we can speed this up. And if you increase the number of GPUs, you can see that communication might become more and more important. And it would be great if we could compress the gradients. So how do we distribute SGD? Commonly, you just send the gradients up, you add them up, and send the result back down to the GPUs. What if we want to use a sign-based optimizer? Send up the signs, that's intuitive. How should we aggregate them? If we just add up the signs, we lose some compression properties because a sum of signs is no longer a sign. So that could be annoying. So for that reason, we propose majority vote. So send back down the sign of the sum of the signs. In essence, each GPU votes on the sign of the gradient, and the parameter server counts the votes and sends back the majority decision. All communication is one bit. And as we're going to see, majority vote actually has really nice theoretical properties. So to reiterate, the compression saving of this algorithm is 32 times less communication per iteration than full precision SGD. So I claim that everybody should care about this algorithm. And here's another reason why you should care about it. The algorithm, in a sense, is very similar to Adam. So sign SGD, here's the update. Take the sign of the gradient. Rewrite this as the gradient divided by its magnitude. That's the same thing. Now look at Adam. Adam starts life exactly the same way, gradient divided by magnitude. until you add you add sort of a perturbation to this algorithm now. Add a series, which is just an exponentially decaying sum of recent gradients. And you can see that adding an exponentially decaying perturbation probably doesn't change the behavior of the algorithm very much. In particular, if you want to understand Adam, the place to start is by understanding sign SGD. And if you like momentum, we have another algorithm which we call Signum, which takes the sign of the momentum. That's the one we're actually going to benchmark in the experiment. It retains the compression property. So why should you care about Adam? If you look at this chart, this is one reason you should care about Adam. This is the number of Google Scholar citations of these algorithms. So Adam, in the 4 years of its existence, has been cited almost twice as the Robbins and Monroe paper, which has been around for 50 years. So it's an incredibly important optimizer in the community. It's very different to SGD. It's sort of less well understood, yet it works pretty well. And like clearly 11,000 people have cited using it. So we should, if we want to understand neural networks, we should understand why this algorithm works so well. Okay. So to reiterate, the motivation for this work is sign descent is been around for a while, has weak theoretical foundations, but incredibly popular. Gradient compression, also, it's not clear why it works so well. The sort of results people get are that you can compress the gradients a lot and not really lose anything in terms of convergence rate in practice. Our work, using the sign, which is what we propose, differs to existing compression algorithms because we say you don't need to care about correcting the bias. A lot of, or I think all of the current proposed gradient compression algorithms take pains to correct the bias in the gradient estimate. We say, don't worry about that, just use the sign. Okay, so we try and unify these and propose sign-based gradient compression. Because this is the non-convex session, we should first build a theory. So we're going to try and build a theory of sign-based optimization. So the first thing, I'm going to propose some considerations which we should make. What should we worry about? We should worry that sign SGD, sign-based optimization, might not converge. That's the first thing we should worry about. Even if it does converge, we should worry about its dimension dependence. If it messes up every single component of the gradient for high-dimensional problems, that could be really bad. Something else we should worry about. We've proposed to aggregate the gradients on the parameter server by majority vote. Is that a good thing? Maybe the improvement by adding machines saturates with majority vote. Maybe something bad happens. We should worry about that. Okay, so what results do we show? First of all, we show that you can make the algorithm converge if you set the hyperparameters in the right way. We characterize objective functions where sign SGD and majority vote are as nice as SGD. What we mean by that is for these objective functions, the algorithm gets the same dimension dependence and majority vote gets the same variance reduction as full precision SGD. This is like a free lunch, compression coming at no cost. Moreover, we suggest that these are the typical functions which you would encounter in deep learning. So this is really basically a very relevant algorithm for deep learning because compression can come as a free lunch. So first of all, we'll give the single worker theory, and then we'll move on to the distributed theory, multi-worker theory. Our results hold under some assumptions. First of all, we assume that the objective function has a lower bound. We make a variance bound assumption where we assume that each component of the stochastic gradient has a bounded variance. This means that our variance bound parameter is a vector where each component is a variance bound for each weight in the network. We also assume a Lipschitz smoothness assumption, which is also coordinate-wise. There's a parameter, a Lipschitz smoothness parameter associated with every weight in the network. These coordinate-wise assumptions are not standard, but they're interesting because they allow you to encode notions of noise sparsity and noise density, curvature or smoothness sparsity, smoothness density, which, as we will see, controls the theoretical properties of sign SGD. So we make some now definitions. K is the number of iterations, and N is the number of backpropagations. The reason K and N are different is because we make use of a mini-batch size, so N is larger than K. And perhaps one of the limitations of the current work is that we have to assume that the mini-batch size is quite large. And in future work, we actually found a way to get around that. But this is sort of a large batch theory. Okay. So under these assumptions, you can show that SGD gets the following rate. I'll help you pass this. So on the left-hand side, we have some kind of average 2 norm with an expectation over the noise and an average over the K iterations. This is the thing that we want to be small. The reason we're using a first-order optimizer is we want to find a place where the gradient is small. So we want to drive down the left-hand side. We get the SGD has the characteristic 1 over square root n dependence on number of backpropagations. So increasing the number of backpropagations drives down the bound on the expected gradient norm. And if we now look inside the square brackets on the right-hand side, there are some constants. Infinity norm on smoothness and 2 norm on the noise. Now let's compare this to what we proved for sine SGD. So broadly speaking, the bounds look very similar. But there are some key differences which I'm going to point out. First of all, on the left-hand side, we get a 1 norm on the gradient instead of the 2 norm. Now on the right-hand side, we get the same 1 over square root n dependence on number of backpropagations. That's like interesting. The algorithm has the same backpropagation complexity as SGD. And in square brackets, we have a 1 norm on the smoothness and a 1 norm on the noise. So the key difference basically is the norms which appear in the sine SGD bound versus the SGD bound. And how these norms compare between the algorithms will sort of inform you about the relative properties of the algorithms. In particular, in the sine SGD bound, there's no explicit dimension dependence. So what could go wrong with sine SGD? If the smoothness is very dense, and if the noise is very dense, we can pick up factors of dimension on the right-hand side, which is like the really bad dimension dependence. This is, so now I've converted the norms to be in the same form as in the SGD bound, but made the assumption that these quantities are very dense and shown that sine SGD can have much worse dimension dependence. But what can save the algorithm is that the same is true of the gradient. The gradient 1 norm can be, if the gradient is dense, can also pick up a factor of dimension. And now you can see that these dimension factors can cancel on the left and right and get the same dimension dependence as SGD. So that's great. So the question we should have is, are the gradients dense in deep learning problems? Before we look at that question empirically, let's look at the multi-worker theory. With M workers, SGD gets the following bound. Divide the variance by square root M. That's why we use M workers. We want to build a better quality gradient estimate and therefore squash the noise. Could we hope for the same variance reduction for majority vote, sine SGD? Under one additional assumption, we can. The assumption is that the gradient noise is unimodal symmetric. As an example, a Gaussian. This is a reasonable assumption in practice by the central limit theorem. If you average gradients over a mini-batch, you expect that things become Gaussian. We'll empirically characterize it in a moment. But under this assumption, majority vote gets the same theoretical speed up as SGD using full. So voting is as good as summing. That's like one of the free lunch results. Okay, so we should have 2 questions now. Are the gradients dense? Because then sine SGD will be relevant. And is the noise unimodal symmetric? For example, Gaussian. Because then majority vote will be relevant. Let's look at these questions empirically. So gradient density. We define a notion of density phi, which is exactly the one which our theory cares about. 1 norm divided by 2 norm. It's normalized by dimension. This is 1 for a fully dense vector and 0 for a fully sparse vector. We measure this, training ResNet 20 on CFAR 10. So here we have gradient density phi plotted against epoch. And we see that for a range of algorithms averaged over repeats, the gradient is within a small constant factor of being fully dense throughout optimization. So this is supporting the idea that gradients are pretty dense in deep learning. Okay, great. So this suggests that sine SGD is a relevant optimizer, theoretically. What about noise symmetry, which majority vote cares about? Here we measure it on ImageNet. In the paper, there's also the CFAR results. And you can see that for 3 randomly chosen weights, the noise distribution of the stochastic gradient basically looks Gaussian, as expected by central limit theorem. This is a mini batch size of 256. So this slide is saying that gradients are dense, noise is symmetric. We expect that sign-based optimizers should work well. So that's great. Okay, does the algorithm scale to ImageNet? Would you really want to use this algorithm? Well, we argued before that it's very similar to Adam, so you would expect that it would work pretty well because Adam works well. Here are some empirical results. So Signum, the momentum version of sine SGD, is the orange curve. Adam is the green curve. And you notice that in all of these plots, and in all the plots actually in the paper, Signum and Adam have extremely similar performance, which supports the idea that if you want to understand Adam, you should understand the sign-based optimizer, which is much simpler and easier to study. Okay, you'll notice that so we have train accuracy on the left, test accuracy on the right. You'll notice that full precision SGD does reach a slightly higher accuracy in the end, echoing recent work suggesting that Adam reaches slightly worse performance than SGD. The optimist will now say that here's an opportunity. If we can either work out how to regularize Adam and how to regularize Signum to squeeze out the same performance as SGD, then that would be great. Or perhaps you would want to use Signum for the first portion of optimization and then switch to SGD at the end of optimization. Basically, generalization is kind of poorly understood. And but the nice thing is that these plots aren't showing you the compression benefits. These are per epoch. So like the proposed way to train neural networks is use Signum with majority vote, get the benefits of compression for the majority of training, and then switch to SGD at the end of training. Okay, performance very similar to Adam. May want to switch to SGD towards the end. What about majority vote? Does that work? This is work with it's not in the paper, but we're working on it at the moment, with a really great undergrad called Jawe. And here we compare 1 worker Signum and 1 worker SGD against 15 worker Signum and 15 worker SGD, training a CFAR model, ResNet 18. And we see that majority vote is getting the same speed up as full precision SGD. So that's great. All communication is 1 bit compressed, but we're not really losing out in terms of convergence. We show you the test accuracy results as well, and you can see that there is some degradation in generalization. Again, generalization is kind of poorly understood, and maybe it would be good if we did some, if we really understood generalization, perhaps we could come up with a better regularizer, or we could switch to SGD at the end of optimization. But to sum up, here's the optimizer. It's just 5 lines of code. It's really simple. Sign-based optimizer with majority vote. My posters tonight, I'm considering screening the World Cup semi-final at my poster. And thank you for listening.
We have about 3 minutes for questions. If people would like to come up to the microphone, please.
Hi, thank you for the talk. I have one concern as someone from distributed systems. I care about unbiasedness. I see that you mentioned the fact that traditional compressed SGD does some additional work to guarantee unbiasedness, but for me, when I want to build a poisoning resilient SGD that I can distribute and be robust to some of the workers being attackers, I care a lot about unbiasedness, and I would really like if you can give a word or two of how could sign SGD guarantee unbiasedness and then be plugged into poisoning or resilient distributed SGD. Thanks.
Thanks. So yeah, one of the messages really of the work is that you don't need to worry about unbiasedness. And I guess I would separate poison resilience from unbiasedness. Actually, the majority voting algorithm is quite intuitively resilient to one of the workers trying to poison you. Take the example of one of the workers sending infinity. With full precision SGD, that's going to wreck everything because all the parameters get sent to infinity. But majority vote quite naturally attributes a certain weighting to each worker. So it has, there's like more properties of majority vote which are nice than I've characterized, but some of them are like robustness to broken workers, probably robustness to adversarial workers. It's just like has really nice properties. Thank you.
Hi. Quick question about the symmetry assumption. So a ResNet has like 25 million parameters, and there's like 1.3 million data points in ImageNet. Can you really expect the CLT to kick in for all 25 million parameters in that setting?
Well, yeah.
I mean, you just don't hope, I don't think you can really hope for concentration of measure in 28 million dimensions with that many samples, can you?
Yeah, I think the central limit theorem applies to all the parameters in the same way. It might not matter. Like one of the sort of intuitions I have is that if things go wrong for a few of the parameters, that doesn't matter. It's what learning cares about is having the majority of the parameters behaving nicely. I see what you mean. Sorry, now I understand the question. But yeah, I think that you want the majority of the parameters to behave nicely, and that should be enough.
Hello. I'm sorry if I have missed this information. Did you measure the overall physical time performance improvement for overall system? I've seen the speed up for network communication, but can you give me speed up for overall training?
Yeah, thanks. We actually haven't implemented the compressed version yet. So that bar chart showing 32 speed up is like I mean, you get that speed up in communication, but it's not clear that that translates into learning. Yeah, we're currently working on a PyTorch implementation of compressed majority vote. If anybody wanted to work on a TensorFlow version, that would be great, and could they get in touch with me? But yeah, we don't have those results yet.
Okay, thank you.
Great, let's thank Jeremy again. Great. So it's a real delight to see so many people here in person, and I think a testament to how well our civilization is working in terms of open borders. However, we do face some restrictions due to politics, and not everyone was able to get a visa to get here in person. And unfortunately, our next speaker, Zeyuan Alan Zhu, was not able to make it due to visa issues out of his control. Happily, though, Ewan here has stepped in and will be playing a video of the talk. And I've been through this video. I think there's a lot of good visual information. We'll be able to have audio that's going to be a little garbled, but I think along with the video, we'll be able to make a good sense of it.
Hello, everyone. Welcome to this talk on practical momentum method for stochastic sum of non-convex optimization. So first of all, let me remind everyone what momentum is in the field of optimization. So consider a simple task of minimizing a function fx that is a convex and Lipschitz smooth, meaning that all of the eigenvalues of the Hessian are upper bounded. So one can apply one of the following two approaches. You can either do gradient descent that converges in rate 1/t, or you can do the so-called accelerated gradient descent method, originally discovered by Urin Esper. So here is how it works. In each iteration, you first try to go in the direction of the negative gradient, and you call this point yk, and then you move to yk plus a momentum factor times yk minus 1. So this is why accelerated gradient descent is also referred to as the momentum method. If you choose the momentum parameter appropriately, say 2 over k plus 2, then you get a method that converges quadratically faster than gradient descent in rate 1 over t squared. To sum up, we have gradient descent, accelerated gradient descent. The latter is quadratically faster, and the latter also turns out to be optimal among the class of first-order methods. But if you think about it, nowadays in machine learning, many of the functions we want to minimize turn out to be non-convex. And even worse, many of them turn out to be stochastic. For instance, when training a neural network with respect to n training samples, then the loss function you care about is the average loss with respect to all the inputs. Then how can we minimize such a non-convex function? We can do SGD, stochastic gradient descent, that has some certain convergence rate, say in terms of finding local minimal. Or in practice, people also do momentum. For instance, people do the atom method, which is essentially applying momentum on top of SGD. But some of you may not know that those momentum methods, all of them, have concrete examples, meaning that there are non-convex functions in which even if you apply momentum, you either diverge or you don't get anything faster than SGD. Therefore, like one question really bothers us a lot in the field of optimization is, first, can we do momentum at all in the field of non-convex stochastic optimization? And if so, then how can we do it in the most efficient way so that the algorithm runs the fastest? So this is not a simple question to answer. But if you think about it, there are even simpler questions than this one that are already sufficiently interesting. For instance, why momentum here and why momentum there? Even more interestingly, there are naturally functions that are maybe not super non-convex, say between convex and non-convex. Then, can we do momentum there? And if so, how can we do it optimally? So this talk is going to be about actually the cases here. First of all, let me first remind everyone about a task that we already have fully understood. That is how to do convex stochastic optimization. For the first thing of all, Nastrup's original momentum method does not work here. Meaning that even if you apply your favorite stochastic method, say SVRG, Saga, or SGD, you apply momentum on top of that, you don't necessarily get something that runs faster. There are counterexamples. But fortunately, there exists the so-called APPA/catalyst reduction, which achieves this rate root n divided by root epsilon. So it turns out to be optimal up to a few log factors along the class of first-order methods. So to give you a quick sense about how this reduction works, it keeps regularizing the objective by a certain amount, and then you try to solve the subproblem, and after you fully solved it to a very high accuracy, you try to regularize it again at a different point, and then you solve it again. So you have to keep doing this like inner outer loop kind of structure of the algorithm, and that makes it not very practical when you apply it to real-life problems. So in our prior work, we developed the so-called Katyusha method that achieves the optimal rate up to constant factor, and it's a direct method. It directly accelerates a stochastic gradient method without encountering the counterexamples of Nastrup's method. So here is roughly speaking how it works. In each iteration of Katyusha, it first applies a stochastic gradient direction. It goes there, and then it applies a Nastrup momentum. So if you only do these two, it doesn't work. There are counterexamples. So what was novel in this prior work is that we applied a third thing. That is what we refer to as the Katyusha momentum, meaning that it moves back towards a point that was a number of iterations ago. So that point, we refer to it as the snapshot. It's almost like a magnet, and then every n iterations you change the magnet, but within the n iterations you keep moving the current point back towards the magnet. So if you add this Katyusha momentum, or you can view it as a negative momentum, then it somehow stabilizes the algorithm to make sure it still converges without encountering the hard instances of Nastrup. So that is a full story about the convex stochastic setting. So in this talk, I want to share with you the story about more complicated problem that sits in between. That is the case when the function fx is convex, but each fi is non-convex. This is what people refer to as the sum of non-convex optimization. So I claim that this class of problems is extremely important for at least two reasons. First, all known versions of stochastic and accelerated methods for PCA, SVD, and or essentially eigen-related problems, eigensystem-related problems, all of those methods rely on repeatedly solving a sum of non-convex objective. And more interestingly, for the only known momentum method for the fully non-convex work also relies on repeatedly solving an objective that is convex, but each fi is non-convex. And therefore, if we can get the efficient and practical solver for here, they also imply better solvers for the subsequent tasks. So for this problem here, in particular, one can also do APPA catalyst reduction. Again, you get an algorithm that is not very practical, but at least you get some good rate, like n to the 3/4 divided by the tensor. So what remains open before this work is that can we design a similar variant of Katyusha so that you can directly accelerate the method without having the inner-outer loop reduction. So this turns out to be possible, and it's precisely what this paper tackles. So here is a full description of how the algorithm works. So first remember how the so-called SVRG method works. Stochastic variance reduced gradient method, how it works. In each epoch of SVRG, it starts from a point W0 and applies some stochastic scheme for n iterations. And in each iteration, it goes in the direction of the so-called gradient estimator. It's an unbiased estimator of the true gradient, but it can be computed from the true gradient at the first point of the epoch, then plus a stochastic update. So I guess most of you have seen SVRG. So in this work, we did not open up SVRG. So instead, we viewed an epoch of SVRG as an independent step, like just moving from here to there. And we apply momentum on the epoch level. That is, we apply SVRG, then we apply momentum. Then we apply SVRG again for an epoch, then we apply momentum. So this method turns out to converge in the rate n to the 3/4 divided by root epsilon. And it also works very well in practice. So if you want to know a little more details here, I can also explain exactly how it's implemented. Remember, Nestor's method looks like this. It can be equivalently written like that. Here is the full description of the new algorithm that we call Katyusha X. In each epoch, it first applies SVRG for a full epoch, and then it applies a modified version of Nestor's momentum. So instead of choosing 2y here, we choose 3/2 of yk, then plus 1/2 of xk. So this might remind you of Katyusha momentum. That is, we are like moving a little bit back towards a point that was a few steps ago. So that was precisely the meaning of xk. So to sum up, we have two Katyusha methods that are very different. They both have some negative momentum flavor, and they both actually support proximal updates, and they both have linear speedup if you do parallelization. So thank you for your attention. If you have more questions, I can be reached here. Thanks.
Since the Ewan is not live, we will be taking no live questions. Do you know if there will be a poster, Ewan?
I don't know.
I don't know. So please feel free to email Zayun if you have more questions. We'll be inviting Jean Gru back up to be our last speaker. You may remember Jean Gru from the first talk of this session. And he'll now be talking about decentralized training and decentralized data.
Yeah, the first author has some visa issue, so I have to speak on behalf of him. Oh. Yeah. Okay. Hello, everyone. This is Shang Rulian. My presentation is about the decentralized training over decentralized data. This is joint work with Hanlin, Ce, Huan, and Zhou Rui and Wei. Let's consider a common objective in machine learning. To minimize the global loss function, which is the average of the loss function of samples from a dataset D. A widely used algorithm for solving this problem is SGD with a single worker. The update rule is just in each iteration subtract from the current parameters by learning rate times the gradient of loss function for a randomly selected sample. For multiple workers, we distribute the data D to n workers, where the dataset DI is on the ith worker. The goal is to optimize the average of the loss function on each worker. As you can see, in centralized SGD, there are two steps at each iteration. First, each worker computes the stochastic gradient based on the current model from the parameter server and send the updated model to the parameter server. And second, the parameter server, which can be viewed as a central controller, will collect all the updated model and average the models. Equivalently, we can send the gradients to the parameter server and let the parameter server update the gradients to the current model. However, for this network design, the parameter server could usually become the system bottleneck for parallelization, especially when the model is large. To overcome the bottleneck of centralized SGD, a new parallelization design, which is called decentralized SGD, has been proposed. In a decentralized network, there's a node parameter server. Each worker would just do local stochastic gradient update and average with its neighbors' models. It can be proved that all the models on each worker will eventually arrive at the same averaged model. For decentralized SGD, we assume two bounded variances. The first is the data variance within each worker, and the second is the data variance among each worker. And the inner variance is called sigma, and the outer variance is called zeta. And this is the convergence rate for decentralized SGD. As we can see, the convergence rate for decentralized SGD consists of two parts. One is related to the outer variance, and the other is related to the inner variance. And this is the term related to the outer variance, and it appears in the convergence rate of decentralized SGD, means that if the workers can access to very different data, then decentralized SGD may converge pretty slow. Our paper focus is on how to remove this part of the convergence rate. In this paper, we developed a D-square algorithm to solve this problem. The difference between D-square and decentralized SGD is that D-square includes a variance reduction term in the parameter update step. The basic idea for this correction term is to use the history information to correct the error generated by decentralized SGD. And this is the convergence rate for D-square. And as we can see, the dependence of the outer variance has been totally removed. To get a more intuitive understanding about why D-square is better than decentralized SGD, let's assume that the model on each worker has already arrived at the optimal value x star. Since the loss function on each worker are different, we have their gradient different, and a local average of the gradients will not be 0. Then for D-square, after one iteration, all the models at each worker will still be the optimal value. However, for decentralized SGD, it will be moved away from the optimal value after an iteration. And this is the main experimental results for D-square. We compare D-square and centralized SGD and the decentralized SGD. In the first row, we deliberately make each worker access very different data. For example, for C14, we have 5 workers, where each worker has access to only the data of 2 out of the 10 labels. In this case, decentralized SGD suffers from the outer variance and admits a much slower convergence rate. On the second row, we shuffle data before distributing the data to multiple workers. And then, in this case, with respect to epochs, all the algorithm converges similar. Thank you. And our poster will be at Hall B 207.
Thank you, Jean-Gru. Let's let a few more people in, and then we'll move straight into the next section, next session on non-convex optimization. And Yuan will be talking about an alternative view. When does SGD escape local minima?
Thank you. So this is joint work with my advisor, Bobby Kleinberg, and my friend Yuan Zhili. We all know that stochastic gradient descent algorithm is much more popular than gradient descent in practice. But why is that? Well, many people would say that it's because stochastic gradient descent algorithm is much faster. You know, in every iteration, it only needs a mini batch of the data set in order to compute the stochastic gradient, while gradient descent needs a whole batch of the data to get the full gradient information. So of course, stochastic gradient descent is much faster. This is an important reason, but do we have any other reasons for showing that SGD is more popular? For example, is the noise in the stochastic gradient useful in any sense? Well, previously, people have shown that the noise would be helpful for SGD to escape saddle points. And today I would like to talk about when it could be helpful for escaping local minima. But before that, I would like to claim that noise is not always helpful. Actually, in some cases, noise makes no difference. This is my favorite example, which I call it the Great War example. This is a very simple one-dimensional function, and it contains a unique global minimal. If we are unlucky and we try to run, say, SGD or GD or any other first-order methods to optimize this function, and we initialize our point here to the left, then it's almost impossible for us to find the global mean because the function does not provide enough gradient information. Actually, for this kind of function, even you are using second order, third order, first order methods, it's still hard to find the global mean. However, sometimes the noise could be very helpful. For example, this is another one-dimensional function. If we look at it from a global perspective, it's pretty close to our convex function. However, there are a lot of noise on this function, so a lot of spikes and local minima. So for this kind of function, if we try to run gradient descent to optimize it, so here is some experimental result. We are running gradient descent algorithm with step size 0.1. And what we do is we try 100 different trials with random initializations. And here the red dots are just the last iteration of the gradient descent for those 100 trials. As you can see, gradient descent could get stuck at almost every local minima. And we also plot the histogram, which is the blue bars here. So it just represents the total number of times the gradient descent gets stuck at those local minima. As we can see, the histogram is pretty flat. That means essentially gradient descent could get stuck at every possible local mean with roughly similar probability. However, if we run stochastic gradient descent to optimize this simple function, This is like stochastic gradient descent with step size 0.1 and the noise level 0.3. We also tried 100 random initializations, and we can see that for every trial, stochastic gradient descent is able to find a point which is pretty close to the global minimum point. And if you look at the histogram is pretty similar to a Gaussian shape, so it's very nicely concentrated around the global mean. So at least for this simple one-dimensional function, we can tell that stochastic gradient descent algorithm is working much better than gradient descent. Here is a nice illustration of what is happening here. If we are looking at the point Wt, for example, we are at this point. And if we just follow the full gradient direction, which we use this red arrow to represent, then we could go to this point Yt. And if we get unlucky, this Yt could be inside a local minimum basin. That means if we keep doing full gradient descent, then we'll be getting closer and closer to the point W circle, which is, could be a bad local mean that we don't want to go to. However, if we are doing like stochastic gradient direction, which is this gray arrow here, it's actually a summation of the full gradient direction plus a noise vector. So this noise vector is this green vector. It will help us to get out of those local minima basin and go to this Wt plus 1. So I say that we'll be getting out of the local minima basin because that if we look at the full gradient at Wt plus 1, the full gradient might be pointing away from the W circle. So we are not go to W circle anymore. Of course, we will not go to using the full gradient direction, but we are always using the stochastic gradient direction, which is a gray arrow, to get a sequence of SGD. So it's from Wt to Wt plus 1 to Wt plus 2. So that's intuition. Well, here is an even fancier 3D plot of the same thing. Like if we initially were at Wt, we could get stuck at this sharp bad local mean, but the noise could help us to get out of this local mean, and then the full gradient could be pointing to another better region. So that's intuition, and do we have any formal analysis? So what we do is we try to look at the updating rule of SGD. So SGD's updating rule is very simple. Wt plus 1 is equal to Wt minus eta times the full gradient minus eta times the noise. So we just split the stochastic gradient into two parts, the full gradient and the noise. So the innovation in our paper is we are not trying to directly analyzing the sequence of W, because that's pretty hard. We are looking at the sequence of Y. So notice that the sequence of Y is purely imaginary. So we never generate this sequence when we are running SGD. We're just getting a sequence of W. But we can always properly and rigorously define the sequence of Yt by doing Wt minus the full gradient times the step size. So from this illustration, it's just Yt here and Yt plus 1 here. It's pretty close to the sequence of Wt. And then by the definition, we know that Yt plus 1 is equal to Wt plus 1 minus the full gradient at Wt plus 1, which further gives us that it's equal to Yt minus the noise minus the full gradient at Yt minus the noise. Well, it's just a very simple substitution. And then if you take expectation on both sides, what we'll get is since the expectation of the noise is 0, because we are running stochastic gradient descent algorithm, it has like 0 expectation. It's unbiased, so the noise has 0 expectation. Then we know that the expectation of Yt is Yt plus 1 is equal to Yt minus some kind of full gradient thing. More specifically, we could say that in the sense of expectation, the sequence of Yt is doing gradient descent-like stuff, but it's using some average gradient of the neighborhood of Yt. So let me say it again, because it's like the main idea of our paper. So it's not using the full gradient of Yt. Instead, it's using the expected full gradient around the neighborhood of yt, while this neighborhood is defined using the noise, which is eta times omega t. So this neighborhood, the size, the shape is purely determined by the noise. If we have this equation, then essentially we could say that the sequence of y is working on the function L convolved with the noise, because it's no longer using the information of L, but it's using the information of L convolved with some noise. And after this convolution, the function L will become more smooth. So here is some illustration. So we are still using the function L that we saw previously. It's like a noisy convex function. If we convolve L with noise level 0.15, here we just using, for simplicity, we are just using uniform noise, but in practice, like the noise could be arbitrary. So, but if we are just convolved it with noise level 0.15, then the function L becomes slightly more smooth. If we convolve the function L with noise level 0.3, it's almost convex, and if we convolve it with noise level 0.6, then it's pretty close to a convex function. It's more and more close to convex. At the same time, if we run stochastic gradient descent algorithm with different noise level, for example, if we run SGD with noise level 0.15, which is corresponding to this L convolved with 0.15, then we could see that in 100 random trials, most of the time, SGD will converge to the global minimum region. However, sometimes it will get stuck at some local mean, which corresponding to the region where after the convolution, the function L is not so smooth or convex. And at the same time, if you run SGD with noise level 0.3, this is the example that we saw before. Almost always SGD will converge to pretty close to the global mean. And because the L convolved with noise level 0.3 is pretty close to a convex function. And if we are running SGD with larger noise, like noise level 0.6, then again, for all the trials, the SGD will be close to the global mean, but the whole convergence region will be pretty spread out. And if you look at the histogram, it's pretty flat. This is because we have large noise in the stochastic gradient. Therefore, like SGD will do random walk and wander around near this region. So this region will be very flat. So that essentially tells us that we don't want the noise level to be too small, because if the noise level is too small, then the function convolved with the noise is not so smooth. And we don't want the noise to be too large, because if that's the case, then SGD may not converge so well. So in order to show this in a more formal way, we need to use a notion called one-point convexity. So this is a slightly weaker notion compared with convexity. So the idea is, if we're at a point y, and we want to go to the point w star, like w star is a nice solution that we want to converge to. However, we don't know this direction. What we know is like the negative gradient direction by stochastic gradient descent algorithm. So if the direction is green, then which means that it's approximately pointing to w star, then it's good. Because by following this direction, we'll be getting closer and closer to w star. However, if it's red, which means it's pointing away from w star, then it's really bad, because it means that we will be getting away from w star if we follow this direction. One-point convexity is just saying that for every point on this function, the negative gradient direction is always green. So it's always approximately pointing to w star. If that's the case, it will be very easy for us to optimize. And here is an illustration of like a function that is one-point convex, and this function is not convex. If you look at the yellow region, this yellow region is concave, so it is not convex. But if you look at every point on this loss surface, the negative gradient is pointing to the center. So this function is one-point convex, not convex. And for every one-point convex function, we know that we just need to follow the gradient direction. We will be getting closer and closer to the final solution. So in our paper, we need to make this our main assumption about the function. The main statement is pretty complicated, but the idea is we assume that if we could do the convolution for the function L with the noise in the stochastic gradient, then the function L will be one-point convex. If this assumption is true, then our main theorem is saying that, okay, so if L is one-point convex after convolution with the noise, SGD will converge near some good solution W star in T1 steps. And then if we keep running SGD for the next T2 steps, it will stay around. It will not go out of the region with probability at least half. And this T2 could be pretty large. Okay. So our interpretation on step size is pretty nice in the sense that by our theorem, we say that if we are using small step size, then the convolutional kernel for the function L will be pretty small. That means we does not change the function L much. So it will not help us to escape the local mean. However, if we are running using large step size, it means that we are using a large convolutional kernel for the function L, and it will help us to escape the local mean easily. However, if we are using large step size by our main theorem, we know that the region that SGD will stay around the W star is linearly proportional to the step size eta. So that means if we use large step size, the region that we will finally converge to will be pretty large. I think this result is pretty interesting because that previously most theory results on SGD only usually require step size to be sufficiently small, which does not really match with our empirical observation. But our results saying that it cannot be too small and it cannot be too large. So finally, I would like to show you some empirical results. So we found that for some deep neural networks, like residual network and DenseNet, with about 1 million parameters, and we tried CFAR10 or CFAR100 as a data set, we try to verify our main assumption to see whether this is true. But our main assumption is pretty hard to verify. We don't know, especially for very high dimensional functions. So what we do is we only try to verify the trajectory of SGD for those functions. So it's not all the region of the loss function, it's only along the SGD trajectory. What we do is we take 100 random neighborhood points for every epoch, and we take 5 random trials for all the model and all the data set. So here is the result. We could see that all the inner products are always positive, which means our main assumption holds for the SGD trajectory for those model and those data set. And also, since we took 100 random neighborhoods for every epoch, by Chernoff bound, we know that this claim that the inner product is always positive holds for with high probability. So at least our assumption is true for the trajectory, so our claim could be useful for explaining neural networks. That's it. Thank you for listening, and I'm happy to take questions.
We have time for one question if someone wants to come up to the mic, and can the next speaker come up and get ready, please?
I have a short question. Simply, how do you control the noise factor? Do you inject additional noise, or it comes simply from mini batches? And if from mini batches, how can you control the noise level?
This is not we are not proposing a new algorithm. We're trying to understand when SGD could use the noise to escape the local mean. And so the noise is from the mini batch, and we are saying that if the noise from mini batch is nice, in the sense that after convolution with the noise, the function L will be more smooth, then SGD would escape. So it's like an explanation. It's not like proposing a new algorithm. So we are not using actual noise.
Thank you. So I have a very quick question. I just wonder what kind of assumptions you have on the noise distribution. You had this, I think that was Xi at some point in the theorem. What assumptions do you have on this distribution?
We don't have the assumption of the distribution, but we assume this distribution will help the loss function be more smooth after convolved the two function. So the noise distribution needs to be nice in the sense that it could make the loss function better.
So that means like you have, I guess, some assumptions on the moments, or like maybe we can discuss later, I guess.
Okay,
Thanks.
okay.
Thanks a lot.
Okay, great. So that talk was about escaping local minima, and our next talk is about escaping saddle points, and we'll turn it over to Hadi.
Thank you very much. Hello, everybody. I'm Hadi from ETH Zurich, and I'm presenting escaping saddle. Okay, sorry. And I'm presenting escaping saddle with a stochastic gradients, a joint work with Jonas Kohler, Aurelian Lucci, and Thomas Hoffman. So in this talk, we focus on minimizing empirical risk objective. The target objective that we consider here is not necessarily convex, but is sufficiently smooth. More precisely, we assume that the gradient map and the Hessian are Lipschitz, and the stochastic gradient have bounded node. So the goal is convergence to the second order stationary point using a first order optimization method. In the second order stationary point, the gradient is 0 and the Hessian is semi-positive definite. So a local minimal example of second order stationary point and strict saddle or not. Basically, we want to avoid strict saddle and escape from them. But one question is whether even it's possible to converge to the second or to the strict saddle using gradient algorithm, using first order algorithm. In this image, you see, in this image on the left side, you see gradient iterate by these blue points that converge into the saddle, strict saddle. So it's possible. But gradient dynamic is highly unstable in a saddle. So if you initialize a little bit of the stable manifold, it will diverge from escape easily from the saddle. So Lee and co-author in 2016 has shown that we can avoid convergence almost surely to the strict saddle by random initialization. However, gradient dynamic may take exponential time to escape from saddle. This idea is formalized by a constructive example in Du et al., Du and a co-author in 2017. So, in this table, what we see is an example of methods can escape from saddle. In all first order methods that you observe here, basically we add an injective isotropic noise either to the parameter or gradient iterate. Okay? More surprisingly are the last two cases where the algorithm is a stochastic itself, but still we add an injective noise. So the question that we consider here is whether we need to add an isotropic noise, or more precisely, our question is whether SGD, the stochastic optimization algorithm, does have an inherent noise to escape from saddle. So we are more interested in training objective of neural network, and we start our investigation with empirical observations. Here in the experiments, we use MLP neural structure The training loss that we use is cross entropy loss. The input is MNIST dataset. And what we do, we randomly initialize the weights. We compute the Hessian matrix on random weights, and we also compute this spectral decomposition. So let Vk be eigenvector associated with eigenvalue lambda k here. So in this plot, what we observe is the distribution of the variance of a stochastic gradient along the spectrum of the Hessian. So for each negative eigenvalue, we have a point in this scatter plot. The horizontal component is the absolute value of the eigenvalue, and the vertical component is basically the variance of a stochastic gradient along an associated eigenvector. So what this plot shows is that the noise of SGD is highly non-isotropic. In a way, and this result also, the non-isotropic of the noise is also observed in paper by Chaudhary and Suato in 2017. So as you see, when the eigenvalue is small and the objective is flat, we don't observe a huge variance for SGD. And when the negative curvature is a kind of sharp and the eigenvalue is large, we observe a large variance there. Okay? So let's focus on this critical direction of the extreme curvature and see how the variance of a stochastic gradients depends along this extreme curvature depends on the network width and depth. Does it change with the depth and the width of the network? So we start from the number of hidden units. So in this experiment, we pick a neural structure with one hidden unit and with different number of hidden layers. We initialize weight randomly, several times randomly, and we computed the variance along the extreme curvature. On the two plots below, you see the box plot of the variance for different number of hidden units, 4, 8, up to 64. And there is a clear contrast here between between an isotropic perturbation and a stochastic gradient. For an isotropic perturbation is blind to the objective structure, and the variance for isotropic perturbation decays as you increase the size of the network. But stochastic gradient still maintain a large variance component on the critical direction even when the network gets large. So we repeat the same experiment for the depth of the network, and we haven't observed a dependency of the variance to the depth neither. So here you can see the variance, the critical variance for the network with depth 4, 8, up to 64. And here we keep the number of hidden units fixed to 10. So, but the question is whether we can prove this theoretically. We can prove this observation theoretically. We started with the simple case of learning half a space, training basically one perceptron. And in this case, if you our theoretical observation relies on one assumption, one key assumption on the loss function. We assume that the loss function, phi, fulfills this condition that the second derivative of the loss is bounded by its first derivative. And under this assumption, you actually can prove that the variance along the negative curvature is lower bounded by a constant factor of the leftmost eigenvalue squared. And the established lower bound does not depend on the number of parameters and also depends on the curvature, on the minimum eigenvalue itself. So after ICML submission, we worked on more complicated structure, and now we have the established lower bound for the network with one hidden layer and one output unit. And this result will be published soon. So, to summarize, so far we observed that the stochastic gradient are non-isotropic. But the noise isotropy is used in the proof of escaping saddle in all methods, all known methods. And the claim is basically also the noise is non-isotropic. It still signals the curvature, the negative curvature that are important for escaping saddle. So based on this intuition, we introduced the CNC assumption on the stochastic gradients that basically says that the stochastic gradients can signal the negative curvature, and we observed that this assumption can be also proven for simple neural structure. And in the rest of the talk, what I want to do, I want to claim that you can replace the perturbation with an isotropic noise with perturbation with a stochastic gradients, or taking one SGD step. So we started from a PGD algorithm by Chijin and co-author in 2017. In this method, basically, we trace the norm of gradient. When the norm of gradient is small, we add an isotropic noise to the iterate, and we continue gradient descent step. And then after certain number of iterations, we can certify the second order stationarity by checking the decrease in the function value. So let's replace the perturbation with an isotropic noise with taking one SGD step. Because of this modification, we couldn't no longer certify the second order stationary, and instead we rely on randomized output scheme that previously used in stochastic non-convex optimization. And we need a little bit modify the algorithm. And using this modification, we can prove that the combination of SGD and GD iterate can converge to the second epsilon accurate second order stationary point in a time that time that scales quadratic with 1 over epsilon, the desired accuracy. Let's compare this result with the perturbation with an isotropic noise. So the iteration complexity that we establish here has worse dependency to the desired epsilon accuracy, but it's instead dimensionality free because we assume that stochastic gradients can signal the negative curvature. That is important and important direction. So we started with a PGD algorithm because it was easier to analyze, but the more interesting question is whether vanilla SGD can also escape from saddle under this CNC assumption. So to address this question, we modified the step size scheme for SGD. Occasionally, we increase the step size to boost the variance along the negative curvature. And using this trick, you can establish a convergence to the stationary point in polynomial time. So in this table, you can we compare the different the iteration complexity of different algorithms. That stochastic algorithm that converges to the second order stationary point. The first two relies on an isotropic perturbation. Again, our iteration complexity is dimensionality free, but is not it doesn't have the best dependency to the epsilon accuracy factor. And for example, the neon frameworks works better using a noise isotropic perturbation. And one interesting question is whether the noise isotropy is necessary for this faster convergence rate or not. So, but here our goal was not to improve the iteration complexity. What we wanted to say is that the neural structure are special, in a sense that stochastic gradients on this objective can signal the negative curvature, and because of this property, you don't need additional perturbation of the noise. And we observed that the noise of a stochastic gradient is distributed highly non-isotropic, and this highly non-isotropic doesn't hurt for escaping saddle. We still can escape saddle with this noise property, but maybe the question is whether this property that observed here can also help for generalization, or can characterize that the local minima that are more likely to obtain by SGD. So thank you very much for your attention, and look forward to see you and talk to you at the poster session.
Our next speaker will come up. We have time for one question or two, if anybody wants to come up to the microphone here in the middle. Okay, we're going to keep things moving along. Thank you so much.
Hi everyone, I'm Dongruo Zhou, and I'm going to present our work, Stochastic Variance-Reduced Cubic Regularized Newton Method. And this work is a joint work with Pan Xu and my advisor, Quan Gu. And we first present our problem setup. In this work, we are focusing on solving these special structure optimization problems, which called the non-convex finite sum problem, where the objective function fx can be regarded as a mean value of an individual component function fi, and for each I, fi can be non-convex. Such a problem is very common in the machine learning area, including the robust regression, deep learning training, and many tasks else. Since each fi can be non-convex, so the fx may be non-convex, and so in general, it will be an NP-hard task to find the global minimizer of the fx. So in this work, our goal is to find an epsilon g, epsilon h approximate local minima x, where the gradient norm of the fx is less than epsilon g, and the minima eigenvalue of the Hessian of fx is greater than minus epsilon h. And to find such an approximate local minima, a very popular method which is first introduced by Nesterov and Polyak in 2006 is called the cubic regularization. In short, this algorithm starts from an initial point x0, and at each iteration, this algorithm constructs a subproblem called the cubic subproblem, which adapts the gradient and the Hessian information at the point xt. And cubic regularization updates the xt to xt plus 1 by using the global minimizer of this cubic subproblem. And in their work, they have shown that under some technical conditions, xt will converge to an epsilon and the square root of epsilon approximate local minima within the epsilon to the power of -322 number of iterations. And as you can see, this algorithm is a deterministic algorithm, and it needs to compute the full gradient and the full Hessian at each iteration xt. Well, such a task will be very expensive if the number of the individual component function fi, which means n, is large, And such task is very common in the modern machine learning area. So to address this computational problem, we propose our algorithm, stochastic variance reduced cubic regularization, in short, SVRC. Our algorithm operates with several epochs, and at the tth iteration of the S+1's epoch, similar to the cubic regularization, we still construct a subproblem called the cubic subproblem. However, instead of computing the full gradient and the full Hessian at the current point, we only choose to construct so-called semi-stochastic gradient VT and the semi-stochastic Hessian UT. And to update our current points, we still compute the global minimizer of this cubic subproblem. And the concrete definition of V and U will be on the next page. So as you can see, to construct the V and U, we need to store some special quantities named reference points, gradients, and Hessian. We will set the reference point as at the point at the beginning of each epoch, and we will compute the full gradient and the full Hessian for this reference point. And in each iteration, we only construct V and U like the formulas. And as you can see, based on the reference gradients and the reference Hessian, we only need to sample the component function fi for bg and bh times. And both in theory and practice, the two quantity bg and bh will be much smaller than n, which will save us a lot of computational resources. And as you can see, another kind of stochastic estimator for the gradient and Hessian would be the subsampled gradient and Hessian. However, unlike the subsampled gradient and Hessian, our estimator V and U has such a special structure, and such a special structure will ensure us that the variance of our estimator are reduced, which will give us a better convergence rate. And now we are going to present our theoretical results. Before that, we need to define two computational oracles. The first is called the second-order oracle, which is short SO. This oracle is that given any index I and a point x, one SO call will return such a triple which consists of the function value, the gradient, and the Hessian for the Fix. And the second oracle is called the cubic subproblem oracle, which in short CSO. And one CSO call will return the exact global minimizer of any cubic subproblem. And with these two oracles, we still need some mild assumption. The first one is called the optimal gap assumption, which assumes that the function value at the initial point and between the global minimum value of the fx is less than a constant. And we still need to assume that for each I, if I enjoys a row Hessian Lipschitz. And with these assumptions, our theorem indicates that with some specific parameter choices, our algorithm SVRC will find epsilon and square root of row epsilon approximate local minima within the SO complexity n to the power of 4 to 5, epsilon to the minus 3 to the power of minus 3 to 2. And the CSO complexity will be the epsilon to the power of minus 3 to 2. And we're going to show this complexity comparison table. And as you can see, it is worth noting that our algorithm SVRC does not need the additional gradient Lipschitz assumption, while the subsampled version of cubic regularization needs this assumption. Another thing is that SVRC is strictly better than the cubic regularization by a factor of n to the power of 1 to 5. And it is even better than the subsample cubic regularization if epsilon is located in a very small value region. And finally, we are going to present our experimental results. In our experiments, we choose 4 cubic regularization related algorithms as our baseline algorithm, including both deterministic algorithm and the stochastic algorithm. Additionally, we also choose another popular second-order method called the trust region Newton method. For the benchmark optimization problems, we choose 3 problems which consist of the non-convex regularized logistic regression, the nonlinear least square, and the robust linear regression. And here are the results of our experiment. And the x-axis represents the CPU running time, and the y-axis represents the function value gap between the current function value and the global minimum value. And the red line represents our algorithm. And as you can see, under this experiment setting, our algorithm outperforms other algorithms. And that's all. And our poster will be presented in this night at Hall B 187. And any questions?
If I could get the next speaker to come up, and meanwhile we do have time for a question or two if people could come to the mic.
Hi, thanks a lot for the talk. So the power of cubic regularization lies in the fact that you can use Hessian vector products instead of computing full Hessian matrices. Is this possible with your variance reduction framework? I can see that it works for linear models, but for a neural network, can you still solve the models based only based on Hessian vector products?
Yeah, actually our algorithm adapts the second order information in 2 aspects. The one is to try to solve the cubic subproblem, which we believe that this kind of action can be implemented more efficient by using the Hessian vector products. And the second one is, as you can see, our algorithm consists of some special structure of this gradient estimator called the V and U. And in this part, I think for the general non-convex function, it is hard to implement the Hessian vector parts into the construction. So, but for some special parts, for some special structure, I think we can implement this efficiently.
Okay, thanks.
Let's thank our speaker again. Next, we'll have Chow, who's going to talk to us about non-convex conditional gradient sliding. I don't actually know what sliding is, but it sounds very exciting, very active, sort of like sledding, but a little less controlled. Okay, great.
Hello, everyone. Welcome to my presentation, non-convex conditional gradient sliding. This is a joint work with
That was a really fast talk. Oh, no? Okay, here we go.
This is joint work with Leah and Xu Huan from the Georgia Tech. First, I will introduce the setup of this problem. We started a non-convex optimization problem with complicated feasible set, where the objective function f is non-convex and L smooth, and omega is a convex compact set. We also consider about the stochastic setting where this f theta equal to the expectation of this f theta psi, and each f is smooth and non-convex. And we also consider about this finite sum setting where each f theta is non-convex and L smooth. Here are some examples in machine learning problem. For example, the multitasker learning problem, where the objective function is non-convex. Here the loss L, and the constraint is a nuclear ball constraint. Here are the motivations of this paper. First, the projection onto this set is expensive. For example, the projection onto the Trianon ball, as we mentioned above, and or it is even computationally intractable. For this problem, existing method in literature is a Frank-Wolf method. It's a projection-free method. Its rate is 1 over epsilon. which is worse than the optimal rate, which is obtained by the natural acceleration method in a convex smooth setting. Lan and Zhou proposed this convex conditional gradient sliding method. Their result, they have the 1 over square root epsilon gradient complexity and 1 over epsilon linear oracle complexity. So here you can see that it saves gradient complexity from 1 over epsilon to 1 over square root of epsilon. So the question is that can we use this high-level idea to improve the gradient complexities in a non-convex problem? So we propose this non-convex conditional gradient sliding method. And the answer is yes, we improve the complexities on the first order oracle comparing with the result on the non-convex Frankfurt method in the batch stochastic and finite sum setting. Here we compared our result with the existing non-convex Frankfurt method. Here the LO complexity means linear oracle complexity, and FO means first order oracle complexity. Here we can see that the linear oracle complexity is same, 1 over epsilon squared, and our non-convex conditional gradient sliding method improved the FO complexity from 1 over epsilon squared to 1 over epsilon. In the stochastic setting, the result is similar. Here, the linear oracle complexity is same, 1 over epsilon squared, and for our non-conditional gradient, non-convex conditional gradient sliding method, we proved the stochastic first order oracle complexities, and we compare result with the Saga Frankfurt method and the stochastic variance reduced Frankfurt method. And our result is 1 over epsilon squared, and we improve the complexities on the stochastic first order complexity. This table is the result on the finite sum setting. Again, the linear oracle complexities are same, 1 over epsilon squared, and for our non-convex conditional gradient sliding with variance reduction, the incremental first order oracle complexity is n plus n to the power 2 over 3 over epsilon. For the stochastic variance reduced Frankfurt method, result is n plus n to the power 2 over 3 over epsilon squared. Let's see some details of the algorithm. Basically, in each iterations, we have some natural method, and we also have this conditional gradient procedure, CONDG. We call this procedure twice in each iteration. Basically, these iterations, this procedure solved a subproblem inexactly with some accuracy eta and chi here. Here are some details of this procedure. Basically, it solves a subproblem using this linear oracle, and until it achieves this accuracy eta. It is easy to say that if this eta is too small, we need a lot of iterations in this conditional gradient procedure. But if this eta is too large, it will affect the convergence of the algorithm, so there is a trade-off. For the stochastic non-convex conditional gradient sliding, basically we use the stochastic gradient to replace the full gradient, but here we need to notice that to guarantee the convergence, we need to use a mini batch of the stochastic gradient. Here we use G bar to represent the mini batch of the stochastic gradient. Here again, we need to count this conditional gradient procedure twice in each iteration. This is algorithm of the non-convex conditional gradient starting with variance reduction. It is based on the algorithm of stochastic variance reduced gradient method. Here in outer loop, we calculate the full gradient once, and in the inner loop, we need a mini batch of the sample and calculate the variance reduced gradient, and call this conditional gradient procedure once with accuracy eta. This is a formal result, theoretical result. Basically, it said that the squared gradient mapping converges with a rate of 1 over n if we choose the step size and that accuracy eta properly. For the stochastic settings, this term says that the squared gradient mapping converges with the rate of 1 over n. And for the finite sum settings, again, we prove that the squared gradient mapping converges with rate 1 over t. And we can use these three theoretical results to get the complexity of the gradient and the linear oracle, and we have already showed the result in that three tables. Here are experimental result. We did an experiment on the multi-task learning in the synthetic and the real data side. Generally speaking, the non-convex conditional gradient starting with the variance reduction converge faster, and followed by the non-convex conditional gradient starting and Frank-Wolf method, and SVRG converge slowly because in each step it needs the projection onto the nuclear ball, so it needs some calculation of the SVD, so it converges slowly. Okay, that's all of my presentation.
Do we have any questions at the microphone, please? Okay, all of our speakers should be available for posters this evening. Thank you guys so much for being here for non-convex optimization. Please enjoy a coffee break.